Welcome. In today's session, I want to discuss the way we build lenses and mirrors. And in the previous session, we discussed the Snell's law and how the electromagnetism implies that how the angles of the incoming wave, the reflected wave, and the transmitted wave relate to each other. And we also discussed the Fresnel coefficients, which tell us about the relative amplitudes or the relative powers of the waves that that are involved, so the incoming wave and the transmitted and reflected waves. So today I want to focus more on the geometry part, or the geometrical optics part, and see how we can build sorry about that, how we can build spherical lenses and mirrors, and how they actually focus within certain approximations. So let's get started. So we will be doing in parallel the reflection and the reflection of a concave mirror and refraction of a convex lens or a convex spherical surface. And we will be doing both in parallel, just so that we know how to deal with both cases. Okay, great. So let's assume that we have a mirror, a perfectly reflecting surface, and that is curved, and the curvature of this is actually a circle. So if we make a revolution solid from this, this would be a lens, a mirror that has a little bit of a spherical surface on it. And let's place an axis, an imaginary line that goes there, so the surface is symmetric with respect to this line. We will call that the optical axis, and we will define a point here which we will call P, which is, let's say, where we place our object. So let's say we want to make an image of, for example, your dog. So you would place your dog here at point P. And the question now is, how does these the rays that emerge, let's say, or that are reflected by the dog, if we want to be a bit more formal, end up, what's the trajectory of those rays after reflecting on the surface of the mirror? So let's draw a ray here which goes in any arbitrary angle, and let's call that angle theta 1. And that one, we know already, it will reflect at the same angle that it at the same angle that it's incident at. So we need to, I mean, this locally the sphere can be treated as a plane. So if we locally follow the ray here in this position over here, it will reflect at the same angle that it's incident at. So it will reflect somewhere around there. So these two angles there, which we will call theta and theta, are the same. Okay, so this is theta. Right. This dotted line that I drew here, gets over here, basically this distance over here from this point to the point over here is the radius of curvature of the mirror. And this point here where the ray ends up, right here, we will call it Q. Okay, so and this point over here we will call it C. Okay, right. And finally, just for the sake of the argument, this point over here we will call it O, the point where the optical axis intersects the spherical surface. Okay, so A few names just for these things. The distance over here. The OP distance. So the distance between the P point and O. We will call S, and we will call that the object distance. So it's the distance with respect to this point where the object lies, and that's object distance. We will also build the distance between O and Q, which we will call S prime, and that's the image distance. So this means that the image of this point lies somewhere in this position Q. Right, and finally the O to C distance, which is this one that I already placed there. We will call it R, or the radius of curvature. Radius of curvature. Right, I will only add now this extra angle that we will use, which we will call theta 2. So we have theta 1 over here, theta 2 here, and theta over here. Now, in addition to that, I will make this construction. I will take a line that is normal to this a green line over here, and that intersects the point C. So this forms actually two rectangular triangles. This one over here, and also this one over here, which share this side over here in red. So for these two triangles, the following relationships will be true. So if we look at this one first, the red line can be written as R sine of theta, and for the other one it can be written as S minus R sine theta 1. Okay, so this is just using this distance as the hypotenuse, this distance over here, and using this angle over here. So now I will make another geometrical construction. I will continue this line over here, and then I will now make this line here normal to this imaginary line as well, right there. Okay, so this is perpendicular there, and now we have formed again a series of different triangles. So we have this triangle over here, this one right there, and we have also formed this little tiny triangle over here. And if you notice, this angle right there, here, is the same as theta 2. So we have theta 2 there. And from that triangle, from those two triangles, this one, the big one, and this little one, what we obtain is that for this case, R sine of theta equals R minus S sine of theta 2. Okay, so in that case, the hypotenuse of the triangle will be this one. Okay, so great. So from these two relationships, we can obtain the following relationship that relates theta 1 and theta 2. So from those two, we obtain that sine theta 1 divided by sine theta 2 will be equal to r minus s prime divided by s minus r. And this equation we will call equation A. Okay, so this is equation A. Okay, right. So let's continue. Right. And now let's continue with the other case that I mentioned. So now let's think of a spherical surface, but now on a refractor, so in a dielectric, let's say glass or any other material, right? So in this case, what we will have is now again a spherical surface there. We will also draw an optical axis right there, and now we will place the object somewhere around here. So let's call that P. We will basically be using the same names that we used before. So let's place the image over here and call that point Q. We will have these place the which we will also call O, and now we have to follow these rays. So the ray that emerges from P is going to go right to the surface, and there what we will have, again, locally this can be seen as a plane surface, at least in that point, if we zoom in enough. And since this is coming at a certain angle, which we will call theta I, that will also refract now at a certain angle that will end up sending us to Q, and that angle here will be called theta R. Okay. Again, if we just continue this line over here, that's the radius. And so on and so forth. And let's say the medium on the left has a refractive index of 1, and the medium on the right has a refractive index of n2. Okay. So we will now build a couple of other triangles. So in this, I will draw one here. So for example, we will have this red triangle right here, right there, and we will have another triangle which I will draw in green over here. So this triangle over here in green. Okay, they both share a side, and we will give names to the angles again. So this will again be theta 1. This will now be theta 2. From this schematic, now we see that these two triangles, which are not rectangular by the way, share this side over here. So from the law of sines, from trigonometry, something we can do is we can get this following relationship. So R divided by sine of theta 1, which is refers to this side, and the opposing angle over here will be equal to R plus S divided by sine of pi minus theta I. Okay, so here we are now dealing with that side over here and this angle over there, okay, which is pi minus theta I. Okay, however, sine of pi minus some angle is actually sine of just that angle. So I will just replace this bit here by simply theta I. Okay, great. Now let's focus on the other triangle, on the green triangle. again using the sign of the law of sines, what we obtain is that r divided by sine of theta 2, so this is referring now to this side in relation with this angle, and will be equal to s prime minus r divided by sine of theta r. So this refers to now this side over here and this angle over there. Okay, great. Right. So from these two relationships, what we can obtain is that from on the one side we have sorry about that. Yeah. So we have r sine theta I will be equal to r plus s sine theta 1, and also we have that r sine of theta r will be equal to s prime minus r sine theta 2. Okay, and by dividing these two relationships with respect to each other, what we obtain is the following. So what we get is sine of theta I divided by sine of theta r will be equal to r plus s sine theta 1 divided by s prime minus r sine of theta 2. Okay. Now let's remember from Snell's law, which we covered in the previous lecture. We know that this side over here, sine of the incident angle divided by sine of the refracted angle, will be the ratio of the two refractive indices. So we have n2 divided by n1. Okay, so from here, what we obtain is that from here we obtain that sine of theta 1 divided by sine of theta 2 will be s prime minus r divided by s plus r and multiplied by n2 divided by n1. And this equation is what we will call equation B. Okay, so this equation B is the one that refers to the length, while equation A is the one that refers to the curved mirror. Okay, great. So everything we've done so far is exact. This means that everything we've found, all these relationships between the angles and the refractive indices in the case of the lens or the refractive curved surface, is the result of just geometrical constructions with no approximation whatsoever. The implications of these and working with this curved spherical surface is that all the rays that come from an object, let's say the point P in the diagrams we just saw, will be bounced off in the case of the mirror or refracted in the case of the lens, but will not form a perfect focus. So each one of the rays that come at different angles will actually end up crossing the optical axis after reflecting or refracting in slightly different points. Okay, and that's called the spherical aberration. And there are books on optical design that discuss it extensively. It's not worth us going into that. However, as long as we only look into the small angles, so angles that are rays that are reasonably close to being parallel to the optical axis, in that case, we can do what is called the paraxial approximation. And the paraxial approximation implies that exactly, just looking at the rays that are close to the optical axis and not the ones that are far away. And in that case, and within this approximation, we can actually form perfect focuses. Okay, and this is what we will do. So we will do now the reflector, and then we will do the refracting curved surface. So I will draw the diagram here again. So we have the optical axis, we have the reflecting spherical mirror. We have the P point where the object is, and we have the normal here, which is a radius, as you remember. And what we will have is that this produces something that looks like that, and here at Q we will have the image, right? So this is just reproducing what we already had. We had some names for these angles, so this was called theta 1, this one over here was called theta 2, and we will add one name here to one point. We will call this point G. Okay, so now if you see carefully, we have this triangle over here, the one that goes from P to Q to G and back to P. Okay, in that case, if we use the law of sines again from trigonometry, we can relate, and let me just use a different color here, this angle over here with this side right here. So these two will have a relationship that is as follows. So we have the distance PG divided by sine of theta 2 it's actually pi minus theta 2, but the sine of theta 2 and pi minus theta 2 is the same, will be equal to, now for example, GQ or QG, QG divided by sine of theta 1. Okay, again this is still exact. Okay, on the other hand, we have we will have that from here we get sine of theta 1 divided by sine of theta 2 will be equal to Q G divided by P G. Okay, and here's where we will apply the paraxial approximation. So we will assume that G, so we will only look at rays that come really very, very close to the optical axis. So this means that G, it cannot be very high. This G point over here, this distance over here, cannot be very high. And if it's not very high, what it implies in terms of PG and PQ is that PG, for example, is going to be basically S1. So within this, if we take the limit when G really is very, very low, the height of G is very low, this one can be approximated by the object distance. So that's S. And this one over here is actually just so QG is going to be the radius. So sorry, the not the radius, just the distance between Q and G, right? It's Q, the distance Q and G, but that's going to be basically the distance between O and Q, and that's what we call S prime. Okay, great. This is again within the paraxial approximation. Okay, so if we combine these with equation A, and let me just go back a couple of slides. So from equation A over here, so if we combine this equation A right here, and what we just did, what we obtain is that R minus S prime divided by R, S minus R is equal to sine theta 1 divided by sine theta 2, which is, in this approximation, S prime divided by S. And from here is that S times R minus S prime equals S prime S minus R. And from here, what we obtain is that 1 over S, if we divide by S, S prime, and F and R, what we obtain is that 1 over S prime minus 1 over R equals 1 over R minus S. And from here, we obtain, I'll change the color because it's important, sorry, 1 over S. It's the following. It's 1 over S prime plus 1 over S equals 2 over R. And if you see, this is the relationship between the radius and the positions of the image and the focal point. Actually, when we take the limit of the object being very, very far, when P is this P point is taken far, far away, what it means is that all the rays will come parallel to the optical axis. And in that case, this means that S is a very large number, and therefore 1 over S is a very small number. And in the limit, what we obtain is what follows. That's 1 over S prime is equal to 2 over R. And 2 over R, or actually R over 2, is what we will call the focal length. So R over 2 is what we call the focal length. It's the position of the focal point. So in this limit, when we take P very far, the image actually falls right in the middle between the radius and this point O. Okay, right there in the middle. And that's where the focus forms. Therefore, this expression that I have here in green can be rewritten as, let's see, as 1 over S, sorry, S prime plus 1 over S will be equal to 1 over F, the focal length. Okay, so this is the equation that we use for curved mirrors in the paraxial approximation. So now what we will do is the same, but now in the case of the refractive surface. So I will again draw the diagram over here. So we have the optical axis, we have the spherical surface, refractive index 1, refractive index 2, which in the case of normal lenses, for example, refractive index number 1 is simply 1, usually is the air, and so on and so forth. And let's put the object here in position P. We have a ray that goes over here to point G, and we have again the Q, the image position, and we have R here, the radius. Okay, so this is a line that is normal to the curved surface. Okay, great. Now again we have the point O here, right at the vertex that we call the intersection of the curved surface with the optical axis. And again, using the law of sines, what we obtain is that Q G, so referring to this one here, I'll just draw the angles again. This is theta 1, this is theta 2, and in this case now we will relate this angle right here, theta 1, with this side over here. So we have QG divided by sine theta 1 will be equal to PG, so this side, divided by the sine of this angle over here. So this will be equal to PG divided by sine theta 2. Okay. Again, same thing. We have that sine theta 1 divided by sine theta 2 will be equal to Q G divided by P G, and this will again, in the case of G being very, very low, so only taking the rays that are close to being parallel to the optical axis, the distance QG is going to be, basically we can approximate it, or will tend to be S1, the distance between Q and O, and PG will tend to be S, or the distance between P and O. Okay, great. Again, this is in the approximation. So from equation B, and let me go 2 slides back. From equation B here, in here, we can obtain the following. Right. So we get S prime minus R divided by S plus R, N2 divided by N1 will be equal to sine theta 1 divided by sine theta 2, and this will be approximately S prime divided by S in this Paraxial approximation. So once again, we rearrange this equation a little bit, and this implies that we can rewrite this as S times S prime N2 minus R N2 equal S prime times S N1 minus plus R N1. Okay. Right, and again, if we divide by S times S prime times R, what we obtain is the following. N2 divided by R minus N2 divided by S prime equals N1 divided by R plus N1 divided by S. And from here, what we obtain is N1 divided by S plus n2 divided by s prime will be equal to n2 minus n1 divided by r. And again, this is so this is the equation for the curved lens and the curved surface, and it relates the object position, the image position, and the radius of curvature, and the refractive indices, of course. So there's a step I'm going to skip here, and it's part of your homework. So what happens if instead of having just one refracting curved surface, you have actually two? For example, something that looks like that. So you have a lens that has two curved mirrors, each one with its own curvature. So the radius of the two surfaces don't need to be the same. So you could have a very curved surface on one side and a very flat surface on the other, but still with a little bit of curvature. Anyway, I will give you the result, and the result is that 1 over s plus 1 over s prime is going to be equal to n plus 1 in the case of the refractive index in the outside of the lens being equal to 1, and n inside the lens will be n plus 1, and multiplied by 1 over r1, where r1 is the radius of the first surface, minus 1 over r2. Okay? And again, in the case where we take the limits of the object being very far, so again, when we move p very, very far, this means that all the rays will come parallel to the optical axis, and in that case, s, 1 over s becomes 0, and 1 over s prime is what we define as 1 over the radius, 1 over the focal length. What we obtain here is that the following relationship, which is also a very, very important one. So what we get is 1 over f will be equal to n plus 1 multiplied by 1 over r1 minus 1 over r2. And this expression over here is the what we call the lens maker's formula. Lens maker's formula, and this one is essentially the equation that we always use in order to calculate the focal length of thin lenses. So this means that the lens is not a curved surface here, and then lots of material, and then another curved surface over here, but more like something relatively thin. Although it has curvature on both sides, it's not a very thick piece of glass. It's actually thin, which is the case of most lenses. And this approximation, again, this is all valid within the Paraxial approximation, but it works very, very well in most cases. Okay, so the lens maker formula, and this is the way we can calculate where the focal position of a lens will be if we know the curvature of its two radiuses, so the two surfaces, and we know the refractive index of the material inside, of course, as well. This is a very important formula in optics, and it helps us design lenses and find what their focal length will be. It's very important. Something I didn't mention is we could use negative radiuses of curvature, and this will imply that, for example, for the mirrors, we have a convex surface, and this means that instead of forming a focus back in the space, a virtual image will be formed on the other side, and as well, we could use concave lenses, and those ones will also form virtual images on the opposite sides and so on. So all of those combinations are possible, and of course I would encourage you to have a look at a book in optics and to study a little bit more. But with these I would like to conclude, and now you have more or less the basic tools in order to be able to calculate lenses and mirrors that produce focuses with spherical surfaces. So thank you very much for your attention, and I'll see you next time.